Hi, let's talk about the direct memory access controller in the array microcontrollers. The DMAC controller is a module that enables transfer of data from one address to another in the memory without involving an operation or interference from the CPU. This means that continuous data transfer is possible, for example, from sensors while the CPU is busy with other tasks. To get started, we will now make a new C++ project in eSquare Studio. On the device selection page, we will choose the EK-RA6M4 board as usual. For the rest of the configurations, we just leave it as it is. As a project template, we can go with the minimal option. Once we click Finish, the project resources will be loaded as per the selections we have made. Once the project has loaded, we can start configuring the peripheral ports. Now, we need two stacks for this implementation. One is the ADC stack, which shall fetch us some analog readings, and the DMA stack, which will coordinate the transfer of these values to a memory address. So, let's find them in the Stacks tab. The ADC stack is found in the Analog menu, while the DMAC stack is found in the Transfer menu. For the ADC stack, we intend to use only one channel, so we don't need to make too many changes to the default configurations. The first configuration is to check the ADC channel mask for the channel we are going to use. Next, we can see that a few ADC channels are already enabled for the ADC0 unit. So, we better disable them to prevent any interference with our channel of interest. We can navigate to the Pins tab and then disable or unassign the pins for ADC0 unit that we do not need. Going back to the stack properties, we can see that all the channels except one have no pins assigned to them. Next, we shall configure the DMAC stack. We start by selecting the repeat mode for this module. Then, we need to attach an activation source to it. This is now attached to the ADC scan operation. Then, we will define a callback function. This function will be used to keep track of the DMAC transfer events. We shall also set the interrupt priority. In this case, we can choose any priority we like since there are not too many interrupts configured. We also define the interrupt frequency to be based on the block or repeat size of the transfer. Once that is done, we can generate the project contents. Now, we will start with the coding part. First, we will import the Sager library files into our source folder. This library allows us to send text data to the PC terminal. We shall use this to log the DMAC transfer notification. As the first entry for the code, we will include the common utilities header files that contains all the references to the Sager library. We will need one variable for this project, and that is to hold the ADC values. The DMA controller will use this variable address as the destination for the data obtained from the ADC buffer. Then we can proceed to the hull entry function. First, we will declare the FSP error status variable. This variable will be used to store the return status of the different FSP calls to be implemented in the next few lines. The first API call is for initializing and opening the ADC channel. We can drag this from the Developer's Assistance menu, and to make sure the function call has been made successfully, we will include the assert macro. In the next two lines, we will define the source address of the data to be retrieved by the transfer unit G_transfer0, which in this case is the DMA controller. So we enter the address of the channel 0 of the ADC as the data source. Similarly, we shall enter the address of the ADC_result variable as the destination point. Once the configuration is done, we can call the API to open and initialize the DMAC module. Then we have to load the ADC scan configurations to the ADC channel. Once that's done, we are then free to start the DMAC module by calling the enable function. In order to fetch data continuously from the ADC buffer, we will implement a while loop. The primary function executed in this loop is a single mode ADC scan. The scan is followed by a 1 second delay. Once each scan has been completed, the DMAC will transfer data from the ADC buffer to the destination variable ADC_result. We will also define a callback function for the DMA controller. This callback function will be executed upon successful completion of a data transfer. We do not need to use any of the event status generated during the DMA transfer, so we can use the FSP parameter not used macro. As we would like to log the successful implementation of the data transfer as a notification, we can send a simple success text to the PC terminal using the Sagar API. Once the coding is completed, we can build the program, and when the program has been compiled without any errors, we can upload it to our board using the debug function. In the debug view, we have access to the expressions tab where we can monitor the value of the ADC_result variable. As expected, the ADC_result variable is fetching the value from the ADC channel. If we attach a jumper from the ADC channel to the 3.3 volt pin, we can see that the value rises to 4095, which is the maximum value for 12 bits. And if we short the jumper with a ground pin, the value drops to 0. We can also check the log messages of the DMAC transfer in the RTT terminal. To do that, we first need to extract the address of the Sagar block in the memory. We can find this information from the .map file in the debug folder. We need to search the string _Sagar. We can then use this address in the RTT terminal to view the log messages. As the messages appear almost in every 1 second, we can conclude that the DMA callback function is being executed after a successful transfer event. So we have reached to the end of our small presentation on the direct memory access controller in ARRAY MCUs. See you in the next video.